Hello, this is Jason Kendall. Welcome to the next of my introductory astronomy lectures. This time we're going to continue on our exploration of the Milky Way, and we looked at the rotation of the Milky Way through the spiral arms. We saw that they were made up of stars and dust and gas, but there's something interesting if we study deeper into the nature of the Milky Way. One of the things that you could ask is that how fast is the Milky Way rotating? And that's a really good question. So let's actually begin really far back and go all the way back to Newton and the apple tree and the grand old thing, but let's go way, way back. And remember the old thing where Ptolemy said that the Earth was at the center of the universe? And the Earth was everywhere, and all the stars and those things were orbiting in spheres and so forth. And people eventually discovered that that didn't work. Mr. Galileo came along and showed that Venus had to be orbiting the Sun, and Mars's orbit could only be explained by elliptical orbits. But still, though, Copernicus tried to place things in a new way in 1543, put the Sun at the center, but still kept pretty much everything else the same. He did this posthumously, so he wouldn't be hanged, so that was kind of an important thing. So Copernicus came up with this heliocentric idea mostly because it was just easier to do. And in a certain sense, you got to admire that, but there's no physical reason. There were a lot of arguments against the Earth moving. So Copernicus said this in 1543 with very little justification. Tycho Brahe came along very soon thereafter and also observed that things were a little different, but he created his own version, combining the Earth at the center, but everything else orbiting the Sun. Makes some really interesting orbital paths. Maybe the Sun and Mars could collide, according to this thing, but Tycho Brahe was trying to figure some stuff out. But eventually, Kepler said this does not work, and so as he was using Tycho Brahe's data about the motion of Mars, he found that the only way to make everything work was with ellipses. And so this is what an ellipse is you have the Sun at one of the focal points, say F1, and it rides along this curve that we call an ellipse. And if it's a circle, then the 2 points F1 and F2 are not at all overlapping, and we call it ellipticity of 0. If it's a very large ellipticity, say 0.4, the foci of the ellipse are very spread apart, and the elliptical path of a planet around the Sun is due to just the Sun at one of the foci. And Kepler said this is how it should be in 1609. This was one of his laws. And so then he also determined that when it was close to the Sun, it moved faster than when it was far from the Sun. And that led him, again in 1609, to declare that the period of the orbit of a planet squared is equal to its average distance, a cubed, for all planets orbiting the Sun. And that works really well, where the period is measured in years, and a is the relative distance between the planets compared to the Earth between the Sun. All right. Newton then came along and in 1687 published the Principia, and in the Principia he detailed exactly how motions work and what all in the nature of the laws of motion. And what was derived using his law of gravity is that you can actually really completely derived the law of Kepler's laws in a new way, where we say the period squared, again now, but this time in seconds, is equal to a cubed, where this time a is in, say, meters. And then you have a derivation that's based on the sum of the two masses that are attracting each other due to gravity, m1 and m2. It might be the Sun and the Earth, or the Sun and Jupiter, or what have you. And g is Newton's gravitational constant, and the 4 pi r squared comes about as a result of the geometry of the situation. But in any event, we have g being the link to gravity. Now, if you measure this thing in years, p in years, and a in AU, then strangely enough, because of these solar units, then the 4 pi squared g m1 or m2 becomes 1, especially if you measure m in solar units. So it's very interesting that you can declare that thing to be 1 in the middle. In any event, this is the true derivation of it, and it shows how the orbit of a planet behaves with respect to Newton's laws of gravity. So Newton's laws of gravity were incredibly important, and we don't underestimate them, because they solved a lot of problems that arose from antiquity, meaning how planets move in the sky. They also solved the problems about how everything moves, and we will use this to great effect now. So now let's say we use another one of Newton's important results is that if you have a central force, something pulling, and the thing that is going around in an orbit is on a circular path, It's just the same as you take a string and you put some heavy thing on the end of it, like a rock or a baseball or a weight of some kind, or you go to the gym, you tie your lock on the end of a string and swing it around. People stay away from you, but you can do that. But then the length of the string holding the lock that you're swinging around above your head like some sort of crazy weapon would be r, would be the radius of the swinging of the thing over your head. And then the mass of the thing is the mass of the lock or the object that you have at the end of the string. Say it's a rock. Say you're going to smash the rock with a can of beans or something, or you're trying to open a can of beans with a rock, and so you're swinging the rock over your head, and you're going to smack it on the can of beans to open it because you want beans. So the m would be the mass of the rock at the end of the string, whose length is r, and v is the speed with which it's going around in a circle, and you square that. So if you take the mass of the rock times the speed that's going around in a circle squared divided by the radius of that circle, and there has to be some force pulling on that string in order for it to go around in a circle, and that's any force. It doesn't matter what's doing it. Some force is causing it to go in a circle. Now it could be, let's just pause it for a second, that instead of a string and an arm, that it's actually gravity. And so if it's the gravitational force, and then we equate the gravitational force to the circular force, we derive this very interesting little equation. Well, we derive this thing based on the if we look at energies, we get a factor of 2 in there. But this says if we have a series of things, so that 2 arises because we're looking at the energy of an incredibly large system of objects buzzing around, not just one thing buzzing around in a central force, but a series of objects with total mass m. Buzzing around at some average radius r, and their speeds are indicated by the v squared again. But that too means that you're checking the average over a large set of bodies. But if we're just simply thinking of one thing buzzing around, or one thing in an orbit, you can get rid of that too. And so there's a relationship between the mass that's pulling on something due to the force of gravity and its speed with which it's going around and how far it is going from that center of that gravity. So, just again, we would find that, like Newton's laws dictate, the farther you are away from a given source of mass, let's say all the mass is situated at the center, and g is Newton's gravitational constant, so it doesn't change, and 2 is just some number, which is the average. It says the average. So the speed that you go around, if you're orbiting at far away from the center of mass, the big M, then your speed will drop off as the distance, this 1 over the distance square root. So that's what you'd expect if something is orbiting another large body of objects. Okay, so Newton's discovery and Kepler's discovery originally in 1609 based on Tycho Brahe's data, and then Newton's reforming of his ideas mean that things orbit in near circles around the center of mass of the object. And the farther away you go from the center of mass, all the mass you orbit, the slower you go. So gravity is pulling on things because of the mass. So the gravitational force says every object pulls on every other object, and the mass is the thing that does that. So, and we can also have another very important thing that we're just going to touch on now, is that light interacts with normal matter if it has some sort of electric charge. So if you shake an electron, like we talked about very, very early on, it will emit light. And if you shake a proton, it does the same thing. So also, if electrons and protons can absorb light because they have electric charge, they can also scatter it. So there's interactions that light can have with matter. So if it has mass, it interacts with gravity. If it has charge, it'll interact with light. And we're going to use that now. So one of our big things that we want to talk about, we mentioned that the galaxy is rotating. We talked about that extensively when we talked about spiral arms. So what do you see if you measure the rotation of the disk of the Milky Way using the Doppler effect on the side of the gases? Well, you find that there are motions. You can get the stellar motions from their absorption lines, and ionized gas has distinct emission lines, and those things are from, say, ionized hydrogen or H2 regions. And there's also other gases in there as well, such as ionized oxygen, ionized carbon, specifically oxygen, neon, and carbon are pretty good. But in any event, the largest maps that we can get are from neutral atomic hydrogen at 21 centimeters, or H1 regions, or neutral hydrogen atomic atomic neutral hydrogen. And so if this rotating object, the approaching side will be blue shifted and the receding side will be red shifted for a rotating glowing thing that has specific wavelengths of light at which it's emitting. So if it wasn't rotating, it would all be emitting at one wavelength. But because it's rotating, the approaching side will have the glowing portion of the stuff coming towards you will be blue shifted, and the receding portion of the emitting light will be red shifted, so it'll broaden it out. All right. Now, we saw from before that the orbital speed of any object around the Milky Way, and the Milky Way is a vast assembly of stars and gas and dust. But the orbital speed of any object, including the Sun, depends only on the amount of mass that's between it and the galactic center. Now, there are perturbations due to the stuff outside the Sun, but those can be mostly ignored because of the huge amount of mass that's interior to the Sun's orbit. And really, the Sun orbits the galactic center, and the average, and if it was smooth and disk-like, then we can ignore the stuff outside because it averages out. There's a lot of stuff on the far side, but it's far away. There's not as much stuff on the near side, but it's close. So that balances out in this diagram. So we really only care about the stuff inside the orbit, which doesn't balance out. So we can measure what's called the rotation curves. And so we'll plot the speed of the rotation of the Milky Way as a function of distance from the center of the galaxy. And so interestingly enough, what we're going to find, since it's not a mystery novel, I'll let you know, the disk of the Milky Way rotates about the center of the Milky Way, and it acts as a center. Thank you. Isn't that fun to have that happen while you're in the middle of something? These people are fantastic. So in any event, I'll leave that in just for fun and enjoyment. The disk rotates about the center of the Milky Way galaxy, and the inner parts of the disk rotate as if it's a solid body, but it's not. The Milky Way is not a solid body at all under any circumstances. So what we have is that but then the speed increase for that portion of it, the speed increases with radius, and the period of the orbit is roughly constant because everything is going around at the same rate like a disk. But the outer parts rotate differentially, meaning as you go further and further out, their orbital speed is about roughly constant. The speed is roughly constant, but the orbital period therefore increases. So chunks one thing lags behind another thing. All right, so this is a graph of what we mean by what we're just describing. In the interior portions, the speed is not constant because it's rotating like a disk. So the outer portions of the inner disk are going faster than the inner portions of the inner disk. So that very, very, very small increase, that steep increase right at the center of the galaxy, at distance roughly close to zero at the center of the galaxy, is very, very tight. But then you'll notice that once we get out to roughly the Sun, it wags up and down a little bit and stays roughly constant all the way out there. This is interesting because notice that little line that says Keplerian motion. We're going to get into what the heck that is. So the outer parts of the speed roughly go about 100 to 200 kilometers per second. The Sun's roughly going about 220 kilometers per second around the Milky Way. But this is interesting. So there's something about those divergent curves on the right that we're going to talk about, which is really fascinating. So what we can do is we can look at this particular graph and determine the mass of the Milky Way, doing all the equations that we looked at before. So once all of the galaxy is within an orbit, the velocity should diminish with distance. So if you see all of the galaxy, or all of the Milky Way is found within one of the orbits, meaning, well, basically everything's inside this orbit and there's nothing outside that orbit, then the velocity should simply drop off because then you're orbiting all the mass. And if you're orbiting all the mass, that's like a planet orbiting the Sun. And if it's like a planet orbiting the Sun, then the farther away you go, the slower you should be orbiting. And that's not what's seen. That's called Keplerian motion. And Keplerian motion is the motion around a body that is very much more massive than the object that's orbiting. Keplerian motion is not seen, meaning it's constant. And in fact, it does rise at the edge. So let's look again at this thing. And so a star or gas cloud is held in its orbit by the mass interior to its orbit. That's the real trick there. So the matter outside makes only a small contribution and mostly perturbs the orbit at best. And so we use Newton's law of gravity and the circular orbit to derive the equation below. And notice we got rid of that number 2, and that's because now we're just looking at a single object orbiting a single mass. And that's basically Kepler and Newton coming together for two objects, an object orbiting another object with a circle. And that's what we're saying here. So the mass interior to the orbit, m sub r, is equal to the speed that it's going around the circular orbit squared times the radius of the orbit divided by Newton's gravitational constant g. So the Keplerian orbit would be what we see on the right-hand side by that equation that we looked at before. If all of the mass of the galaxy were included inside the orbit, then it should drop off as the inverse square root of the radius of the orbit. But it doesn't. So it should fall, but it doesn't. The reason it should fall is because if we're seeing all the mass, if we know about all the mass, then it should drop, but it doesn't. So that's very interesting. But it shows a flat rotation curve out at extraordinarily large radii, like double the distance of the sun from the center of the Milky Way. It keeps going up and up and up. It stays flat. The only way for that to happen is for the amount of mass in the disk to grow at the same rate that the radius grows. So there is just as much mass, there's more mass as you go out further and further and further. And that's the only way for this to occur. So you have to have more mass in order at a given radius. There has to be more and more and more mass in order for the speed to stay constant. That's what this means. So the g is a constant, it's Newton's gravitational constant. 2 is that number that comes from averaging over a large bunch of particles. M is the total mass interior to the orbit, and r is the radius of the orbit. So for v to be constant, the mass must be proportional to the radius. And so if the radius grows, the mass must grow. All right. As an example for the Milky Way, and specifically for the Milky Way, at 8 kiloparsecs hot was where the sun is, the rotational speed is 220 kilometers per second, and the mass interior to it is about 10 billion, or about almost 100 billion solar masses, which is a huge number of solar masses. Now, there are measurements of gas clouds way out in the outer disk, double the distance that the Earth is from the sun, and its speed is actually a little bit higher. It's 275 kilometers per second, and that means the mass interior to it is almost 300 billion solar masses, which is a lot. It's not 10 billion, not 100 billion solar masses, but 300 billion solar masses. So it's a huge amount. 30 billion, actually, I'm sorry, not 10, 30 billion solar masses. Whoops, I'm reading things wrong, aren't I? So it's 30 billion solar masses. 300 billion solar masses. Wow, I really shouldn't have a Montauk beer before I do all these things, shouldn't I? In any event, we measure the rotation speeds in spiral galaxies, and they provide us a great way to measure the masses of these galaxies. The point is you see more mass as you go out, no matter what. All right. So this leads us to the following 3 pictures of the Milky Way. The interior is solid body rotation, meaning, well, the speed is proportional to the distance. Remember, it's not actually a solid body, but when you have a lot of mass packed into a very, very, very small and dense area, it can interact such that it is a solid body. The interior area of the Milky Way is not solid, but it can behave that way. However, we should expect that once you're outside it, you should have Keplerian rotation, meaning you have all the mass interior to it, so it should drop off as inverse of the radius squared. But what's actually observed is the galactic rotation at the bottom, which is the speed is roughly constant. So there is unseen mass. And what do we mean by unseen mass? And let's look very carefully at this, because it's important to actually clarify what we mean and actually prove this with actual data, because that's what we do in science. We actually take data and support our concepts with data, or more specifically, we make a measurement and then try to explain it. And this is the data from Clemens in Astrophysical Journal in 1985. And he made a plot of the rotation curve that's found from carbon monoxide, H2 regions, neutral hydrogen regions, and globular clusters. And we find that much past the 8 kiloparsec radius of the sun, that the data points don't go down. They're scattered, certainly, but they seem, on average, pretty constant as we go out. You have to really average it, and so you smooth it, and it's definitively not dropping to zero. It's certainly not dropping Keplerian-wise. It's certainly going to the right and staying constant, and that's what we mean. This is dark matter. This is evidence for the existence of matter that doesn't do light. And what do we mean by that? Here's a picture of a galaxy that's very similar to the Milky Way. So let's pretend that this is the Milky Way for a second, stand outside it, and you get about 8 kiloparsecs out, which is about 2/3 the way out. And we find that looking at radio emission from H1 region, neutral hydrogen regions, that it still is spinning much past the bright spots. The bright spots are where stars are lighting up the gas and dust, and they're stars, they're really bright. But then there's neutral hydrogen that's really cold, really dim, and emits only in radio light. So that's what's being measured way out in what looks like the dark region. However, if the stars traced the light, if it was only the stars tracing the light, then you should get the red band. But no matter what, that should be it. However, because it's a constant or staying constant, then the measured speed of things that are far, far, far out there is constant, which means there's more mass that you don't see that's not in the form of hydrogen, which is really interesting. All right, so the average of those three things put together indicates that there must be some sort of unseen mass deep out, way out in there. We start off with a very, very dense region. That's the solid body rotation. That's very dense, close into the core of the galaxy. And then it does try to drop off a little bit, but then there's something else that starts to kick in, and that is the dark matter. Something keeps it from dropping off as Keplerian. There is more mass that is unseen that causes it to spin, to go at the same speed when it should be dropping off. All right. So if we look at other rotation curves of galaxies, not just the Milky Way, we see this to be a very common feature. Each of these graphs comes from Begeman et al. In 1991. There's a number of studies of other rotation curves, and we see that there's 3 different curves plotted together, and if you add them up, it actually shows you what the component of dark matter should be. The dark matter halo is the dashed dot line, and that dark matter halo is apparently gets larger as it goes further and further out. In fact, what we find is that it's mostly stars and gas and dust in the center, and the luminous components are the dashed components, and the dotted components are dots. So you've got a dash thing, which is like stars, gas, which is the dots, and those things contribute a certain amount of the speed of rotation. But then the full total rotation is the curve going across the top. And that's really interesting that you can separate these things out and find what should be due to the gas, what should be due to the stars. And you have to have some component that's neither gas nor stars in order to replicate the actual data that is discovered by looking at rotation curves of other spiral galaxies. And here's another set. This was by Vera Rubin in 1978, and this is one of the more important areas of her work. And she also labeled the different kinds of spiral galaxies, SA, SB, SCs, and types like that. It doesn't matter the kind of spiral galaxy, they all have these flat rotation curves, which means every spiral galaxy has huge amounts of dark matter. And even if we look at cosmology, meaning the entire universe, we had discovered that roughly of all the entire energy density of the universe, about 23% of the entire energy density of the universe is dark matter. And this can be seen by many, many, many different methods, like say how much mass is there compared to the light. It's a mass to light ratio is what they're measuring. And no matter what, the mass to light ratio says, well, how much mass is there compared to the amount of light there is? And each measurement shows that no matter what, there's a significant amount of dark matter. All right, so what is this dark matter? If it's made of normal stuff, like normal elementary particles that are like protons and neutrons, that would be like brown dwarfs, Jupiter planets, black holes, neutron stars, white dwarfs, primordial black holes, maybe even just puffballs of frozen hydrogen that got stuck out into space. Who even knows? There's lots of things that it could be. But this would just be normal matter. And all of these things would be called massive, compact halo objects, or MACHOs, which is a really fun thing to call them. But massive, compact halo objects are amazing, are an interesting possibility. So let's go look for them. So how would you actually look for them? If a MACHO passes between the Earth and some distant star, then as it does so, the light that would go in one direction gets bent gravitationally by that object and gets redirected towards you. And so you get what's called gravitational microlensing that briefly magnifies and brightens the star. So you have, the background star. So some dim thing that you cannot see goes in front of a star by pure chance, and it has a perfect alignment so that the light that comes from the far star gets microlensed by the near dark object. And so people went out and hunted for these things and actually found a few. And this is kind of a better view of what it sees. All of a sudden the star gets brighter in the background, and these things have been seen. But the problem is that it takes a huge amount of time, and you have to look at a lot of things because it's extremely rare, because stars are really tiny objects. They might be bright, but they're extremely tiny, and you have to get exactly the perfect lineup to do it. So over 6 years, a particular group looking for MACHOs looked at millions of stars for half a decade, found only about a dozen or so halo microlensing objects by looking directly at the Large Magellanic Cloud or the Small Magellanic Cloud. And worse than that, because you can say, well, it got brighter by this amount, you can measure the mass, and that's a general relativity thing, and that allows you to say that they're small. They're roughly about the size of Jupiter, up to maybe typical white dwarfs. However, you can't make up most of the mass of the galaxy, because if that was making up most of it, then there should be a huge number of these things, but they simply don't occur in huge amounts. So MACHOs cannot be the amount of things, which means that normal baryonic matter is pretty much out. So what do we think they are? And so if you go hunting around and go checking what are the best things they are, and so now you're starting to talk some weirdo talk, right? Okay, what's dark matter? Right now, the wisdom of the internet says, as of summer of 2018, there's basically five top things, and none of them are normal matter. All of them are like these crazy things. One of them are WIMPs, or weakly interacting massive particles. So these would be normal matter that doesn't interact with light and doesn't interact with the weak nuclear force. They just don't do anything. Kind of like a neutrino, but maybe something else. But nobody knows really what they are. So what are they? They're WIMPs. Nobody knows. And next, well, axions. Axions are even more fun to talk about, because quantum mechanics has some very strange things with respect to quarks, because exactly how do quarks come together to form protons and neutrons? And so a theoretical particle is devised, created, made up out of thin air in order to solve an unsolved problem concerning quarks. So maybe axions exist, and that's kind of like, well, we don't know, but something's got to keep them protons together and them quarks together. And in threes, that's kind of what quarks do. So what's an axion? Well, it's helpful for that thing, but so let's go hunt for it. Maybe it's dark matter. Ooh. So people are hunting for axions. Next is ultralight scalar dark matter, which is a really weird thing. This would be similar to axions, except their mass is so incredibly tiny, so insanely tiny, that their de Broglie wavelength would be thousands of light years long. And then you have another thing, which is like we know of three versions of neutrinos, and we talked about the sun. There were neutrinos coming in the sun and exploding supernovae. That neutrinos come out of the sun rapidly, and they're produced by nuclear reactions, and as they travel through space, they oscillate between the three different flavors. Maybe there's more flavors. Maybe there's an alternate group of neutrinos that are much more massive than the normal triple of neutrinos, and they only would interact with matter when they flip between flavors and not while they're actually a particular kind of sterile neutrino. So you might have sterile neutrino, big bear, little bear, and mama bear, papa bear, and baby bear. Right? Whatever they are. They don't interact with anything until they wonder where the porridge is, and then they interact like crazy. So sterile neutrinos. Then you have self-interacting dark matter, and currently that is the most attractive thing to researchers now, meaning take all the normal matter that we have in the universe and make it dark matter, and you have lots of different dark matter particles. They just simply don't interact with any normal matter except through gravity. And so that's kind of like the Star Trek mirror world, but with dark matter. It's kind of a strange thing. All of this stuff is extraordinarily speculative, and this is a result of the fact that dark matter is an observational thing, and so many ad hoc explanations are created in order to explain something that is that is absolutely necessitated because of that. Many people like to say, well, let's modify Newton's law of gravity because that's a lot simpler than trying to find things that just sound weird, because a lot of people look at this and go, this is garbage. Let's just modify gravity. It'll be easier. Make a new equation. But there's a lot of things that say that modified theories of Newtonian gravity don't work. In fact, there's a lot of predictions of modified MOND things that do not work. So that's kind of out, and that's very much on the downside. It was pretty popular about a decade ago, but not anymore. All right, so dark matter halos. What is the source of this extra mass? If it's not stars and not gas, the galaxies have these extraordinary extended halos. They might contain up to 90% of the galaxy's map, and they're even more extended than the starlight component. They may even go way out to 200 kiloparsecs or greater. So these incredible halos of dark matter surround individual galaxies. And the dark matter, just because it doesn't interact with anything, can't collapse. It can't lose its energy and fall under the influence of gravity. So since it's hot in a way, it must stay hot. And by hot, I mean has big orbits where it's moving fast and can't collapse down into groups. So light and normal matter can emit its energy and collapse and fall into structures like galaxies, but dark matter cannot, so it stays extended. So we find that the Caltech astronomer Fritz Zwicky in 1933 also went and looked at clusters of galaxies, and he found that they were moving extraordinarily fast, maybe thousands of kilometers per second relative to the cluster center. And that's much greater than the escape velocity if you added up all the stars and all the clusters of the galaxies and just looked at the clusters. And he said there must be some component of dark matter, and in fact Fritz Zwicky was the one who created the thing. He called it dark matter, but actually in German it is dunkles Materie, and that's kind of a great thing to say. So there must be the extra gravity, and therefore if in galaxy clusters there must be almost 100% of it is dark matter, which is really amazing. Okay, so we do know, however, that about 10 million, there's this enormous amount of X-ray emitting gas in galaxy clusters, and in fact, this gas is so hot that it's moving so quickly that without dark matter, the gas would dissipate extraordinarily quickly, and we can see the evidence for this dark matter because of gravitational lensing of background galaxies by the clusters. So this, with galaxy rotation curves, means there's a huge amount that we do not see. So let's look at that X-ray emitting gas, and here is something from the Chandra X-ray Observatory. On the right is an optical image of the Perseus cluster of galaxies from the Blackbird Observatory. On the left is a Chandra observation of the Chandra X-ray Observatory observation of the Perseus cluster core, and we see this enormous amount of X-ray emission on the left, which is the center of that. Now that's a huge amount of gas. In fact, it composes more of the hydrogen than all of the galaxies combined. But even still, it's too hot and moves too fast for it to actually stay in this group. It's moving too hot for its light level of mass, or it's not massive enough in order to hold itself together, so therefore there must be dark matter. And then we go to look at galaxy clusters and gravitational lensing. And if you look closely at these images, you'll see these arcs, these arc-like structures. And these arc-like structures are formed as a result of the gravitational lensing by the dark mass as the light from distant galaxies passes through the gravitational field of the cluster of galaxies. And this is galaxy cluster Abell A1689, and it was taken with the Hubble Space Telescope Advanced Camera for surveys. And there's a Chandra X-ray Observatory version looking at Abell 383, another galaxy cluster, and we can even see X-ray versions of these things. So the purple glow is the outline of X-ray emission. So we have an X-ray emission on top of what appears to be an image taken by not an X-ray. The purple glow is the X-ray, and the starry sorts of images that the galaxy sort of images is from the Palomar Digital Sky Survey of the rest of it. So there's an enormous amount of hot intercluster gas, but it is too hot and is not enough mass to stay together at its temperature. And it's not enough mass there to hold the galaxies in place either. And this is called the El Gordo, which is another X-ray emitting galaxy cluster, and we have other galaxy emitting clusters as G351.03. Well, very interesting names in X-ray. But we also think that much of the gas is primordial, means it dates from the early days of the universe, 13.6 billion years ago, 13.4 billion years ago. But there's not enough in it to become from the galaxy clusters themselves. So how do we know? So can we map this in any way? And yes, we can. And here's how we do it. When you go to see an eye doctor, say an ophthalmologist or even an optometrist, and you want to get new glasses, what they do is they put a series of lenses and they make images and they look at images on the surface of your retina, and they focus images on your retina, or basically specifically focus their view of your retina on their view, and they're really close up too because they want to see what that image will look like. So they want to measure the distortion that's caused by your lenses of your eye. So what you can do is do that in reverse. And by the simple process of, an optometrist would say, oh, so we have a distortion of the background galaxies. They're distorted into little arcs. So what do you have to have in order to distort them? So what is the shape of the lens? Meaning you've got something that's causing a change in the lens. And so you can think of this as a gravitational lens. And in fact, we think of ray tracing, and we can trace the light back to its source. And then we ascribe a certain amount of gravitational pull to that, which demands a map of a dark matter. So this purple glow here is now no longer the map due to X-rays that Chandra saw, but rather a derived map based upon the appearance of the cluster, how fast the galaxies are moving, and the gravitational lensing that's embedded inside, that surrounds and embeds the entire cluster itself. So this is an enormously rich galaxy cluster, as you can see, Abell 1689, which is this huge group of galaxies. Our Milky Way is not even close to such a group. We'd have a very different view of the night sky if we were. But in any event, all these galaxies are in this big group, and something's holding them together, and that something is a huge amount of dark matter, and that dark matter is shown in purple, but it's derived through computer simulations, and then the derivation of that computer simulation is overlaid on top of this Hubble Space Telescope image. That's the same for this image, which is the classic bullet cluster. And what we're going to have is that it's three separate images overlaid. We have one which is a visible image, which is the kind of the stars and galaxies sort of image. Then we have the red image, and that's the Chandra X-ray Observatory, which shows where the hot X-ray gas is. And then we have the dark matter map, which is the blue. So the X-ray gas, when these two clusters of galaxies passed through each other, the X-ray gas interacted because it's distributed widely, and it got hotter and formed into these funny bullet shapes. But the dark matter doesn't interact with anything, so it keeps the galaxy clusters together even as the galaxy clusters pass through. So the X-ray gas gets left behind, and then the clusters move on without the X-ray gas. And here's a better picture of that version. So once again, this is a visible light image overlaid with the red X-ray Chandra image, which shows where the X-ray emission of the ultra-hot intercluster gas is, and then the bluish stuff is the derived map of where the dark matter must be such that the galaxy clusters stay together as they passed through each other. And this is a similar situation to the musket ball cluster, where the red is again the X-ray emitting gas, and we see a series of galaxy clusters, and it's called the musket ball because there's a series of Well, there's a series of ball-like structures, and I guess that works for anybody. And we see where the gas has been left behind as the two galaxy clusters have collided and moved on. And we have another one where the dark matter is mapped in blue, the X-ray emission is mapped in red, and it's similar to the bullet cluster, but it's now been mixed a little bit as the two clusters have moved on to the right and to the left as they passed through each other billions of years ago, or it took billions of years for them to cross that vast gulf of space. And the galaxy and the dark matter just keeps them together. They're not mixing. But the intercluster gas is left behind because it interacts with itself and self-gravitates and collides, just like any gas cloud would. So the gravitational lensing occurs all over the place, and we can see that this gravitational lensing also provides another indirect measure. And here's examples of gravitational lensing here and here with very high redshift galaxies. And in fact, we see them in many different things. And here's an extraordinarily striking view of a galaxy cluster where we see lensed galaxies deep in the distance that look like arcs. And that is one of the more amazing appearances. We've kind of gone over this a couple of times, but this is Abel 1689 once again, and let's kind of zoom in on a few of them. And the part of the reason for showing these images is that, wow, you don't get to see these things very often, I'm sure. And this is part of the reason, is that these images need to be more publicly seen. And I like this one a lot, a galaxy cluster Abel 370. Almost everything in the fuzzy objects are all galaxies. But off to the right, in the upper right, is a highly distorted galaxy image. And that galaxy image is projected across the sky in two different locations. And we see that the upper left and the upper left and the lower right are the same exact galaxy, but across the galaxy. And in fact, we see the upper left is, to me, the most interesting of the bunch, because the image of the galaxy, which is behind all of the other cluster galaxies, the light from that distant galaxy, which is very, very bright, got redirected to our eyes perfectly by it's such that well, not perfectly, because it got all smeared out and everything. So we have multiple images of that distant galaxy being smeared out by the foreground galaxy. And here it is, the last one away. And this is a Abel 370 so this galaxy cluster is about 5 billion light years away. And we're looking at something extraordinarily distant that is much farther away than the galaxy cluster. This is kind of off to the side of the galaxy cluster, this image. But the smeary tadpole thing is much further than the galaxy cluster. It might be 5 or 10 billion light years even further away, which means we're looking at something that's very, very distant. If it's 10 billion light years away, then we're seeing something that's 5 billion years older than all of the other, or 5 billion years younger than all of the cluster, the galaxies in the cluster that are in the foreground. And we can see some evidence for the earliest nature of a galaxy in this thing, that they're very strange and small and bright along their lines. And we see huge, bright, starry features in this galaxy. But it has multiple images, and they've all smeared around into this tadpole shape due to the distribution of dark matter in the galaxy cluster that alters the path of the light. All right, so that's an enormous, enormous overview of the nature of dark matter in our Milky Way and beyond. And I could have left a lot of that stuff for much later in the course, but I figured dark matter is such a really interesting topic. I'd take some extra time with it, and as a result, I have a lot more review questions for you to go over and take a look at. There's a whole bunch, but you can do them as you want. But what we really think is that dark matter actually does exist. And the hard part about dark matter is that all of the things that might make up dark matter are very strange sorts of things. They aren't normal matter in any sense of the word. They can't be most of the matter can't be normal atoms or molecules or planets or white dwarfs or anything, because they're just not numerous enough. And people have been looking for them. So they must be some strange, weird subatomic particle predicted by the standard model or the extended model of particle physics. They might be there to solve some crazy problem in quantum mechanics or something. And so there are a number of active searches for dark matter candidates, and I'll post some of those links on the YouTube channel, the links below. So we really do think that most of the matter in the universe is actually dark matter and not normal matter. That's the real trick with this. So we're going to see what that means when we get to cosmology. See you next time.